A black hole can keep a galaxy alive. How is that balance possible? Immediate takeaway: the universe stays calm because push meets pull everywhere. Picture jets lancing from a galaxy's heart while stars quietly orbit. Gravity gathers matter while energy feedback and expansion spread it out. Nothing wins forever, so extremes burn out before they run away. That rhythm shows up from star nurseries to superclusters. We can actually measure it in speeds, temperatures, and densities. When one side overshoots, the other side pushes back. That seesaw keeps structures stable for billions of years. Today, I will show how that cosmic truce works. We will track forces, flows, and heat budgets across scales. You will see why the sky looks surprisingly orderly despite chaos. Picture a gigantic cube of space, larger than any galaxy. Zoom far enough and the clutter fades into a gentle pattern. Cosmologists call this idea the cosmological principle, plain and simple. It means the universe looks statistically uniform and directionless when averaged. You care because predictions work only when randomness cancels on average. Expansion stretched early wrinkles, while gravity grew structure from small seeds. Dark energy slowed growth later, so patterns never ran completely wild. The microwave background glows almost perfectly even, with tiny temperature flecks. Those flecks are about 1 part in 100,000. Count galaxies beyond 300 million light-years, and densities stabilize. Surveys measure a clustering strength called sigma 8 near 0.8. Hubble's constant sits near 70 kilometers per second per megaparsec. Together, those numbers tell us the canvas really is smooth. Local lumps exist, yet disappear when you average on huge volumes. Rule of thumb: chaos fades fast once your box is gigantic. Takeaway: the big picture stays balanced because noise cancels out. Galaxies can cluster, but overall space keeps a steady texture. We can trust averages there and build solid physical models. Bottom line: scale up and balance emerges from statistical smoothing. Stand between a galaxy cluster and the empty dark beyond. Inside, galaxies orbit a common center. Outside, everything drifts away. Hubble expansion means distant space grows, stretching the gaps between islands. This matters because it decides which structures can actually survive. Gravity binds nearby matter, overcoming expansion within a critical region. Beyond that turnaround radius, recession winds and neighbors become forever farther. Mechanically, 2 numbers set the contest: mass and expansion rate. Higher mass deepens the well, while Hubble's speed sets the tide. Today, H0 is about 70 kilometers per second per megaparsec. That means a galaxy 10 megaparsecs away recedes near 700, yet the local group stays bound, moving around 200 kilometers. Virgo cluster's core remains intact, despite its outer members drifting outward. One-sentence recap: bound beats drift wherever gravity owns the neighborhood. So galaxies, groups, and clusters persist, while voids keep expanding. Picture stars swarming through a dark halo, like bees in wind. Virial equilibrium means motions balance gravity, keeping the system steady. Care about this because it sets sizes, temperatures, and lifetimes. As matter falls inward, random speeds rise, converting potential energy to heat. Collisions, turbulence, and mixing spread that energy through stars and gas. The system jiggles until kinetic energy equals half the binding pull. That balance locks in a characteristic radius and velocity scale. In the Milky Way, circular speed sits near 220. Halo mass lands near 1 trillion suns, give or take. The hot corona reaches a few million degrees, glowing in X-rays. Dwarf galaxies show the same rule, just at smaller scales. Bottom line: jitter and gravity settle into a long-lived truce. Now watch a starburst city ignite, then blow its own fuse. Feedback is energy returned to gas, which changes future growth. It matters because unchecked collapse would burn fuel far too fast. Supernovae dump heat and momentum, stirring and thinning star-forming clouds. Radiation pressure from massive stars pushes dust, carving channels for winds. Black holes add jets and outflows, which can heat whole halos. A single supernova releases about 10 to the 44 joules. Thousands together drive winds at hundreds of kilometers per second. Active galactic nuclei can outshine galaxies, then quench that very fuel. M87's jet inflates cavities, heating surrounding gas and stalling new stars. One-sentence recap: outflows prevent runaway collapse and keep galaxies breathing. Across a galaxy, gas is always arriving, leaving, and returning again. The Baryon cycle is that traffic regulating star formation rates. It matters because supply and pressure decide a galaxy's long-term color. Cold streams fall along filaments, feeding disks with fresh fuel. Stellar winds and jets blow back, lifting metal-rich gas into halos. Some of that gas cools later, raining down to light stars. In the Milky Way, stars form near 1 to 2 yearly. Inflow rates appear similar, within a factor of about 2. Winds carry comparable mass, giving a mass loading near unity. Typical recycling times are hundreds of millions of years. Text Q: inflow, outflow, recycle, repeat until fuel reaches balance. Bottom line, the traffic light controls the pace, not the crash. Drift over a galaxy cluster where hot gas fills the space. Cool core clusters shine bright in X-rays, yet rarely overcool today. That phrase means the center wants to cool fast, then flow. You should care because unchecked cooling would build monster galaxies. Jets from the central black hole heat the gas on repeat cycles. Buoyant bubbles rise, stir, and spread heat through sloshing and sound waves. Turbulence moves energy sideways, while gentle shocks top up the core. Perseus shows ripples in X-rays, tracing thousands of repeated outbursts. The injected energy rivals tens of millions of supernovae over time. Outbursts happen every tens of millions of years, keeping pace. One sentence recap: heating matches cooling closely, so the core idles. Watch a proto-galaxy spin up as rivers of gas pour in. Angular momentum is the tendency to keep spinning, unless torqued. It matters because spin sets disk size and halts full collapse. Nearby structures twist the inflows, handing over spin during assembly. Inside, turbulence, feedback, and bars redistribute that spin through time. Too much spin, the disk spreads; too little, the core grows. Our Milky Way turns near 220 at 8 kiloparsecs. Its disk scale length sits near 3 kiloparsecs, give or take. Simulations find a dimensionless spin around 0.04. That small number is enough to save disks from collapsing. Bottom line, conserved spin provides a quiet brake on gravity. Feel the background coolness, a faint bath near 3 Kelvin. Entropy is the tendency for energy to spread out. This frames cosmic balance as dynamic, not a frozen stalemate. Hot objects dump heat into colder sinks, raising overall disorder. Stars and black holes speed that spread, while gravity creates pockets. The microwave background sits at 2.725 Kelvin. Space keeps expanding, so the background thins and cools further. Star formation peaked about 10 billion years ago, now 10 times lower. Galaxies still cycle gas, yet the faucet is slowly closing. Rule of thumb: order thrives locally, while disorder wins globally. Net result: balance lasts ages, but the evening always cools. That black hole keeping a galaxy alive suddenly feels less magical. Push meets pull, heat meets cooling, and spin puts on brakes. Across scales, the universe buffers extremes, then settles near balance. If this clicked, consider subscribing for more calm cosmic deep dives. Thanks for watching and for staying curious with me tonight.